Hello. Am I audible?
Go.
Yeah, we can hear
Thank
you.
you. Okay, so today we'll talk about testing. Next week we get to talk about ethics, which is always fun. Before we get into the details of the slides for testing, be aware there are such things as standards. So I'll post this on the discussion page. This just lists a bunch of different standards. ISO, International Standards Organization. They control, they advise pretty much all of the world's engineering in some form or another. So even when you have a national standard, they'll attempt to make it match the ISO standard. And that way, when you want to import your product to another country, you generally are already certified or well on your way to certification in that country. There's many ISOs. You can see here, this ISO 2500N, 25001234, right? So right away, there's 5 different divisions right off the bat. Each one of those, they have an N there because they may be further subdivided. I'm bringing this up because when you leave here, when you leave school and you work in industry, often you are required to work some specific standard. If you get a contract that's offered by the, in the US, any level of federal government, they're going to say, here's the standards you have to meet, here's the standards you have to use. So one of the goals of the of our curricula when students go through it, at least make you aware that standards exist. And for some of the critical ones, make you aware of what they are. So for example, next week, we'll talk about the IEEE ethical standard in a little bit of detail. But here's a group of standards. There's also, these are IEEE documents that you see here. The DoD has their own set of documents, often prefaced with MIL for military. So when I did testing of physical things, it was MIL Standard 810. When I was doing strength and ductility of materials, it was MIL Standard 5. So be aware that these things are out there. Sometimes you think you're getting lucky, you look at a standard and it's really short, it's like 10 pages long. And then unfortunately, all it is a list of all these other standards that you have to meet in order for that standard to apply. And now you're stuck with 400 pages of documentation or more. So we have, just look at the titles here. For a standard for format of documents in different stages of software testing. Methodology for establishing quality requirements. Software verification and validation plans. Unit testing. Software verification and validation. Now that's different than the plan. That's the actual verification and validation. Software inspections. We talked about inspections as part of the quality assurance discussion 2 weeks ago, last week. And remember things like walkthroughs and inspections, right, where you have teams actually looking at the code. Well, there's guidance for all this stuff, basically best practices. Even this, classification of software anomalies. So be aware, there are standards, they are out there. In your capstone design, they will encourage you to use at least some standards. And it's always a good thing when you're going on a job interview to say, oh, we did this class project. Well, a class project has a pretty high variance in terms of quality. So was it a class project where you guys just kind of BS'd your way through some software? Or was it a class project where you actually used some kind of process and you actually held yourself to some standard? So if you're saying, oh yeah, well, we did this class project, oh, and we used Agile Scrum for the Scrum Guide, and we used, the IEEE Code of Ethics, we used IEEE, 830 is our guide for requirement specifications. These kinds of things are helpful to have in your hip pocket. Just another page, similar. These were not hard to find, right? These are ICO, IEEE, similar stuff. Um, the FAA, if you're dealing with aviation-related software, the FAA also, not surprisingly, has their own set of standards, and they have their own set of standards for software verification and validation, software quality assurance. They have a slightly different viewpoint because they put a large focus on safety because people die when airplanes crash. And they also have quite an interest in real-time systems because, of course, aircraft are real-time systems. You know, you can't tell that aircraft to just, why don't you just hover in the sky for a while the computer gets back to you. So they have a slightly different perspective, and their systems talk about that. Standards on top of standards on top of standards in industry. And when we talk about, gosh, why did the agile system come up? It was a reaction against the heavy documentation that was being done on software projects in the past. This is kind of part of that, right? You still have to figure out, okay, how am I going to convince the customer if they require that I meet these standards? You know, how am I going to convince the customer that I've met these standards? And often that means you bite the bullet and produce the documentation. So in your spare time, there's some fun reading for you. People who are taking this class, by the way, some of you are, a fair number of you are taking a minor. So that means you're actually getting an aero degree or a civil degree or a mechanical degree or some other degree. These kinds of fields exist in all engineering disciplines. So for anything to do with electronic systems, IEEE tends to have the standards for that. But anything that has to do with physical things, then you're going to be looking at what, ASTM and MIL and other organizations that are producing these standards. There's even standards for academia. That's what accreditation is all about. All right, so if you weren't aware of that, now you're aware. Not educated, but aware. All right, testing. We've all done testing. Every one of you has done some kind of testing on your software. Is this true?
Yeah.
Yeah. How did you do your testing in class, like for a class assignment?
So for 225, I would like run the code and see if it printed what I wanted to print or did what I wanted it to do.
Okay. And in 225, I asked people to write a few requirement specifications just so they get the hang, just so they have some experience with it, and then to write specific test cases for those requirement specifications.
Yeah, there was a plan.
And since all of you took 225, most of you with me, hopefully you actually performed that activity. If not, you got a ding on your grade somewhere. The way people do software in academia, and this is true even for research projects, unfortunately, is really ad hoc. When you're writing for a homework assignment, most people for their homework assignment will not think about a real test case. They'll do, well, it seems to work, right? I ran it and it ran and it didn't crash. And then the next level up is a project where you're actually strongly encouraged or required to develop a little more formalism, writing requirements, writing test cases. I've been able to meet with groups last week. So, you know, my encouragement is always, before you start writing code, your team should agree on some requirements and some test cases so that you know that when the code is completed and it passes those requirements, you have a better chance that the code is correct. You're still not guaranteed correctness, but a better chance that the code is correct. So it gets more formalism. And this is the kind of stuff, by the way, when people start out from high school and they want to go into software engineering or they want to go into computer science, and they think, oh, this is really cool, I want to develop software, but they don't think about what all the processes are behind it. So the actual writing of the code is a relatively, the smaller chunk, right? If you think of all the work you have to do, the actual writing of the code is the smaller chunk. And even in the agile world, it may be the majority of the chunk of all the work, but it is not 95%, right? 99%. It's only a slight majority. This is true in other engineering disciplines too. So, you know, you want to be a civil engineer, you want to be an aero engineer, that's all great, but the amount of time you spend actually doing the work of the working with the equations or, you know, verifying that a design is good is a smaller chunk than you would think when you probably first entered university to study the degree. Remember, we review each other's work and we have to maintain standards and meet these requirements, and we have to produce documentation that showed we did that. And then someone has to verify your documentation. So it's all about, you know, it's a lot about process, and then the work becomes part of the larger process. So the same thing is true with testing. By the way, I hope, and I notice this is a flaw in the course, right? So if I teach this course again, I'm going to add a section about this. I hope people are using automated testing tools. It will, you know, initially there's a learning curve there, but it will save you time in the long run. So if you're using Eclipse to develop your code, I hope you're using JUnit testing. Even on GitHub, I think we found that there's a way to do unit testing and automated testing on GitHub. Some people are using Unity. There are almost certainly tools that would interface with Unity, and if not, you can just do some. It's not that hard to hand tool your own tests and your own test plans, and your own capability to keep running tests every time you change the code. So I hope that is happening in the teams, and as I meet with the teams, you know, I find out more about that. I don't hope because it's a goal of mine. I hope because it really makes your life easier. How many people are using JUnit testing, by the way? Any? I recommend you look it up. It's not hard to learn. It integrates easily with Eclipse. And in fact, it used to be, I haven't looked at the Eclipse tutorials for a long time. It used to be the very first Eclipse tutorial was, we're going to build a simple class. And they actually built the JUnit test, and then they put some test cases up, and then they built the class afterwards, which I thought was an interesting thing to do on a first tutorial. Look into that with your teams. It will give you value. Okay, two main kinds of testing, white box and black box. What's the difference between the two? What's a black box in general? When people use that term, what do they say? Black box is only input and output, right? And black box in any engineering discipline, when people talk about a black box, they're talking about something you can't see inside of. So you don't know the guts of it. You don't know how it's constructed. All you can do is watch how it behaves. You know, you can poke it with a stick. So in terms of software, if you don't know how the software is constructed, all you can do is feed it inputs and watch its outputs. And you would have an expectation of how the inputs and the outputs should align. When you get really formal with this stuff, this all goes back to CS222. And in CS222, we talked about relations between sets, and there was an input set and an output set and a function that defined a relation between the two. Well, that's what your software is doing, actually. Your software is defining a relationship between all possible inputs and all possible outputs. And since that relation can be formally defined, you can perform, you can take advantage of that and then decide what inputs are pertinent to you and what the output should be. So that's black box. Well, if black box means you don't know what's the structure of the code looks like, guess what white box means? You guys are too energetic today. Yeah. So if black box means you don't know what the structure of the code is, white box means you do know what the structure of the code is. Now, since all of you are developing your code from scratch, you know the structure of the code. So you can perform white box testing, and you're more likely, I would think, to perform white box testing. You can take advantage, because you know the structure of the code, you can take advantage of that knowledge and construct your tests in such a way that you have achieved some kind of criteria with regards to testing. And we'll talk about that, what that testing is, or what the criteria are. You know, the basic ones are, I want every line of code to be executed at least once, or I want every conditional to be tested for both a true value and a false value at least once. Those kinds of parameters you can set up, or those kinds of targets you can set up, and then you can set up your testing plan in such a way that you get that coverage. Okay. The two different verifications approaches, static and dynamic. This is just a reminder from what we talked about before. Static is going to be your inspections and your walkthroughs. And today we're going to talk about the dynamic, which is the testing. Software testing is a critical element. Let's see. Have any of you guys taken CS332? I can't always get my name straight. No CS332 people? We talk in there about Turing machines. I talk some in there about Turing machines and, you know, what Turing proved. And, you know, what Turing proved was a big deal. What Turing proved is you cannot write a computer program who will take as input another computer program and then tell you if the other computer program was written correctly or not. That's the bottom line of what Turing said. The bottom line is he said some things are not computable, but the prime example that he used for non-computability was, can I design a computer program that would take in another computer program and then tell me or verify without running the other computer program, just analyzing it statically? Can I have that? Can I determine what that input computer program is doing and not doing? In other words, can I verify its correctness just by observing it, not watching, not executing it, just by going through the lines of code? And what he proved is you cannot create that computer program. So you cannot create a computer program that will gobble up another computer program and then and say, yep, it's all correct. You know this for a fact, because if that was true, you wouldn't do testing. If the opposite was true, where you could write such a computer program, you wouldn't do any testing. But we all know testing is part of software development. So again, think of your evolution as a coder. You start out coding either in class for a first time or as a hobby, and you're not writing down any planning, you're just coding, right? You just start, and then you want to see if it compiles and want to see if it runs, and you play around with a couple different test cases and you kind of shrug and you're like, oh, okay, looks good. That's right. That's what most of us do when we start out. And then people start telling you, really annoying things like, maybe you should plan what you're going to do before you do the programming. And maybe you should put out these things called UMLs, or maybe you should put out user stories or, functional definitions of what you want this thing to do. And so you get a little more formal. And as you keep progressing in your skill level of programming, hopefully you're progressing in your skill level of both planning and designing the software and verifying that the software is both valid and verified to be correct the way you wanted it to be. And then you get into the more sophisticated forms of testing. You actually start to be more formal with your testing. Oh, okay, I want to write, these 5 tests, and my homework assignment, I'm not going to turn it in until it passed these 5 tests that I've already written down. Most people, most students, right, when you're doing a simple homework assignment, you're not going to go through that effort unless it's required. So why don't you do that? I mean, you personally, what's your personal motivation? I'm making an assumption. First of all, I'm making an assumption that you don't. So why don't you? Number one. And then what would happen if you did? Number two. No thoughts? It's too time consuming to test everything. But do you test anything? I mean, formally, or do you just run it? Okay, compiled and at random, turning it in. Yeah, and that's called being human. You got a lot of classes, you have short on time, you got a lot of commitments, you're going to get your homework done, you're going to turn it in. Do you hand your code to another person to review? Hey, you mind reviewing my code? No. Would your grade be better if you did? Would your grade be better if you handed it to someone for review or made test cases ahead of time? Oh, I think if I pass these 3 test cases, I'll feel comfortable that my homework is at least, not out of the ballpark. At least it's going to be, relatively good. Yeah, your grade would be better. So it's an effort issue. Now, we talked a few weeks ago, by the way, about software design and how much time should you spend in software design and software, planning, and how much time should you spend. And I said then, it's really hard to prove that good planning saves money. It's really hard to prove that. And why is that? Because the money that you didn't spend on something is invisible. It's always the money you did spend. Oh my God, that program, the F-35 is hundreds of billions of dollars over budget. That's visible. That money is visible. But if someone was saving money, there's no way to really account for that. So you're experiencing that on a small scale. So it's hard to convince your management, oh, you need to give me 2 more weeks of design. And I promise you after those 2 weeks, which is going to be a lot of money, 2 weeks. But in the long run, I promise you it will save you money. And at the end of the project, they don't see any saved money. All they see is they spent money till the end of the project. Even though maybe you really did save them money, it's invisible money. It's the same thing here. It's hard to convince yourself that it's a good idea to do, even on a simple homework assignment, a little planning on how you're going to verify your homework assignment before you do the homework assignment. So most people will start coding. Maybe with some homework assignments, you'll do some sketching ahead of time. It's tough, right? You're all pressed for time. We're all pressed for time. And so it's tough to convince yourself that there's value in doing work that is not directly producing code. You're experiencing it. But once you create the code, how do you know it's right? Well, testing. Well, if you didn't have a good test plan going into this, you're probably not going to have a good test plan at the end after the software is written, and you got to turn the homework in 10 minutes. That's probably not going to happen. Yeah, we never stop planning, but yeah. Well, in industry, here's what they said: never time to do it right, but always time to do it over. Right? That's how that worked out. So, yeah, software is never done. We know that. Yeah. So, how do you know? Well, testing. Now, even with good testing, remember there's a flaw in this. You cannot test to prove that the software is 100% correct. All you can do is test to the point where you say, well, I didn't find any more defects, but you can't prove that there's not a defect hiding in there somewhere. Right? You can't prove there's not a snowball in the desert. There shouldn't be a snowball in the desert. Well, in the summertime, at least. There shouldn't be one, but you can't prove it. So we're looking to see if the program has any errors, and of course we can't, number one, we can't analytically prove it. We can't do a scanning software to prove it. So we're going to go testing, but it turns out with testing you can't prove it either, because you can't do all of the billions and billions of test cases that would have to be created, even automatically. You know, we've talked about combinatorial explosion before, and you know, you're supposed to deliver your software in 6 months, and if you did all the test cases, even automatically, it would take 10 years. You know, so there's literally no way to get around that problem. So what do? You come up with what you hope are good techniques for testing, and then you say at some point, well, we didn't find any bugs. We passed these requirements. Therefore, you know, the software passed all the tests. Does that mean that it no longer has any bugs in it, no longer has any defects? It does not mean that. And that's why after you deploy your software, someone's going to hack it and steal all the credit card information from people, and you were sure you had that thing secure, and it just wasn't. It doesn't take much time to watch the news to find software hack, software hack, software hack. Okay. Now this one is a rather unusual point of view. Look at that second bullet. A successful test is one that uncovers an undiscovered defect. That's a different point of view, isn't it? We normally think of, well, wait, we want to pass the requirement. We failed the test. Yeah, the test that you pass on the first try, it's not pointless, not 100%, but when you say that you passed the test, does that mean that you can guarantee that there was no other bug that you didn't test for? See, so it's a one-way, sadly, it's a one-way street. If you find the bug, if you find it, then you know that you found a bug. That's actually a very positive thing, because now you can go back and correct the code. So in that sense, it's a successful test because it helped you improve the product. It discovered a flaw that you would otherwise have not found. But if you pass the test and you didn't find the flaw, that's good news too, but there's no guarantee that there's another flaw hiding somewhere, right, that you just didn't catch, you didn't test for. There was some unique set of circumstances with the input conditions that you chose that buried that other bug, right? Because you can't test them all. So that second line I like, because it kind of is counterintuitive. It's definitely counterintuitive to the way most people think about pass fail. The bottom line is, and actually I get this a lot with CS225. Oh, what happens if I fail a test? Oh my God. And people won't report if they fail a test. And I'm like, no, if you don't report that you fail a test, then you're going to lose points. If you do the test and you don't pass the requirement, or the test quote fails, then, and you report it, that's the job I'm asking you to do. That gets you, full grade coverage, because that's, People don't like to report failure, right? You got to report success, you got to report failure. And in the case of testing, they're both successful in the sense that if it didn't pass the test, you were successful because you found a bug. And if you did pass the test, you were successful because there is an apparent belief that the software is good. No guarantee, but at least more confidence. We're not going to walk through this because we've got a lot of slides today and I'm taking up time on the early ones. We're not going to walk through this. We're basically going up to the third column, system functional requirements. We are not dealing with other software requirements, user environment, these kinds of things. Those are later on down the road. And in fact, that was a question in a team meeting. Yeah, I'm focusing on functional requirements for your test cases, for your projects. Okay, then we have unit testing. What is unit testing? Well, don't you build your software in units, especially in the object-oriented world? In the object-oriented world, you build things in classes. The classes have methods. Then they start to interact with other classes, other methods. So unit testing is at the small level. Integration testing is when you take the smaller thing and you start packaging it together with other things. The unit testing is probably the most common thing. Well, you test at least for functional testing, I should say. You're testing at the unit level, this thing kind of floating out in space, and then you're going to take that piece of code and integrate it with the main code and test it again there. Is it possible that if you wrote a class and you wrote a testing method in the class and it passes and then you integrated that class into the rest of your code, that same test could fail? We should get an example of that, shouldn't we? Yeah, it's possible. It's possible. Again, this term is not unique to software engineering. This happens in all forms of engineering. You have an aircraft with a whole bunch of avionics boxes on it. And they do unit testing on the individual avionics boxes. Then they put the avionics box in the aircraft and they test again. And maybe they'll test the whole aircraft, but they'll test that thing again in place. Well, it worked on the bench. Why won't it work in the aircraft, right? Is that useless spending of money? No. Because once you're in the environment with other things, you can be affected by those other things. So you might have an avionics box that works great on the bench, and then you put it in the aircraft and it turns out it's, I don't know, being affected by the radar unit or something like that that's on the nose of the airplane, or it's being affected by the nearby avionics box, and now it doesn't work anymore. So that's the difference between unit testing, systems testing. Most of our work is done at unit testing level. Again, the good news about using these automated testing systems is when you develop your test for the unit system and then you start to do integration, you can just automatically run these tests again. That needs to be added to this course as a specific thing. Here's an interesting view, maybe an interesting view of what testing is actually all about. You've got on the left, black balls are failures and program crashes. Let's say white balls are successful. So in the one on the left, black balls, now these are inputs. So every possible input that you put into the program always fails. And on the right, every possible input you put in the program is always correct. The reality is a typical program has mostly white balls and some black balls in it. And your job as a tester is to reach into that bucket and pull out balls and see if you can find all the black ones. So you see, this is a statistical problem, right? The only way you could actually guarantee it is to pull them all out. But as we've talked about before, the combinatorial explosion does not allow that. So if you think of it from a statistical model, then you can start to think in terms of, well, statistically speaking, what would be enough samples to get a good sense of what's happening here? And that's when we get into coverage. Oh, execute every line, execute every path, execute every decision point, these kinds of things. So that's what testing plan is about. How do you get a good selection? Black box, white box. If we look on those pictures on the right, there's not much difference other than under white box, the test cases. Notice you have specification and program, right? Under white box testing, you can test outside the specification. What does that mean? Well, the way we do functional testing and the way with the unit testing, if you're doing white box testing, then you can test things that are not specified, and you can determine ahead of time what you wanted the software to do with that. So you can run test cases that are not and you can also run test cases that are not part of, quote, program behavior, because you can test individual methods at a time, individual lines of code at a time. Whereas in black box, you're stuck with the whole unit, right? You input, output for the whole unit. We're all looking for the same stuff. And the lines that are important here: exhaustive is not feasible and ad hoc is just gambling. So you want to have a real test plan. Okay, so white box. What's a basic block? In a piece of software, what's a basic block? You just repeat the slide. By the way, in EGR 115 or CS 223, did they talk about basic blocks? In 225, I don't cover it, I know. But in EGR 115 or CS 225, do you remember that term? Nope, okay. All right, so here's the basic thing. And this terminology comes from prior to object-oriented software, when programs were thought of more in the, start at the beginning and go top down. As you know, you start at the beginning and you go top down, and then you have decision points where you can branch either left or, true or false, and you have loops. Well, a basic block is a single block of executable statement that once you get to this statement, you have to do this one, this one, this one, this one, and this one. It has to happen. That's a basic block. And so you can take your code, which has, maybe hundreds of lines of code or thousands of lines of code, but you chunk it up into basic blocks, and then you can represent it graphically based on how the basic blocks relate to each other. Well, first we do this, then we either go true or false, and we do this basic block. Once you're in the true branch, you have to do these lines of code. So that's what a basic block is. And it helps you abstract away all the detail of the code when you're doing some of your planning, as we'll see in a second here. So here, basic block. Oh gosh, what lines? What do we have here? This is clearly a top down, right? It looks like it's Pascal, which is a language that's not too popular anymore. So you begin at line number 1 and you go line by line by line by line by line. Okay. And on line 5, we have an if statement. And on line 10, we have a while statement. And on line 14, we have an if statement. So, but once you get to line 1, and you look here, once you get to line 1, you have to go to statements 2, 3, 4, and 5, right? Those have to execute. 2, 3, 4, and 5 have to execute. And then if the line 5 is true, you're going to go to line 6. So there's a basic block right there. It's just one line. If you get to line 6, you have to do line 6. And then if line 5 is false, you're going to go to line 8. So that's another basic block. So this is just a listing of all the basic blocks, where you enter them, where you exit them. Now, why do you care about that? Because if you want to do your, we're going to talk about coverage in terms of testing. If you're going to do coverage where you want to execute every line of code, you have to make sure that you're hitting all the basic blocks. If you want to make sure that you're doing what they call path coverage, then you want to make paths from these different basic blocks and make sure you cover all of those. So how do you do that? You do something called a control flow graph. Now, I would hope a control flow graph is a term you've heard at this point, but I don't know if that's something that's taught in 223 or EGR 115. And if it is, do you remember? Because those courses are starting to be a while ago, right? Any recollection of this? In 223, I thought Behe had you guys do flow graphs when you're laying out your code. Is that true? Yeah. So, and what he was doing really was a control flow graph. And how about in EGR 115? Did they have you graph stuff or did they have you do like pseudocode algorithms? Or is nobody here from EGR 115? Yeah, okay. All right, so that's what he was having you do is the flow diagram that you did was control flow. You can make other graphs that are data flow. What a surprise, right? But let's focus on control flow. So the control flow is showing you the branching points, the if then else, and the loops, right? So you take the basic blocks and you can break them up into, I'm going to skip this for now, there. And you can break it up into these graphs. So here we have read, that's 1 and 2, and then 3 is a while, 4 is a pointer was set to false, 5 is an if statement, 6 is a set pointer to true, and 7 is down. Let me get down here. Sorry about that. So 7 is, a math op, and then 8 is a math op, and 9 is result. So what's happening here is you start out with 1 and 2 reading in some kind of a data, you go to line 3, and as while something is true, you do 4 and 5. Now, once you get to 5, you either go to 6 or you go right back to, or you skip 6, right? So either you go to 6 or you skip 6. That's what that join is. It's joining the 2 branches of the if then else. And then once you're done with that, you do 7 and 8 no matter what. And then you go back up to 3. And if that's true, you keep doing that. Now, every time through, you might skip 6 every single time, or you might go to 6 sometimes and sometimes not. Every single time through is different. Finally, when the whole thing is done, it spits out to line 9 here and prints the result. So that's how you can create these control flow graphs of actual code. Notice what's happening. Hopefully the control flow graph was presented to you as a way to plan your code. This is actually creating the graph after the code is produced. So after the code is produced, you can create these graphs. Now you can build software that will do this. You can build software that will automatically, reads in a program, automatically makes the graph for you. That's doable, and it's very helpful. So then you have to ask yourself, we'll get to this point. Oh, if I was testing this, how would I want to test it? Oh, okay. Depends on the coverage we want to get. Every line, every path, every decision point. Here's a slightly different one. Notice these. This is a loop inside of a if then else. So you start out with 1, and then if since 1 is an if, the Boolean test, if it's true, you go to 2 and 3, and you keep looping through 2 and 3 for a while. And if 1 is false, you go to 5, and then 5 and 6 loops for a while. And eventually, no matter what side you're in, those will stop, and so they join up that way. But if you look at the code, you can convert it to that graph. Now, notice, let's see. 2 and 3, let's pretend that that loop was bigger. While, and instead of just line 3, there was 10 lines of code in there. You can, this is where basic blocks help out. You can just represent that as one chunk in your control flow graph. So the graphical version of the code looks a lot quicker. Same kind of trick here. I'm not going to go through them all. You can go through them on your own. But the idea is you can write these control flow graphs that show all the different paths that you can take through the software. And then you say, what kind of testing do I want to do? I can do statement coverage, branch coverage, condition coverage. What is statement coverage? Every statement gets, oh, this is the advantages and disadvantages. Well, let me talk about that before I go into the coverages. Sorry. The advantages and disadvantages of white box testing. Here's the good news is because you know the structure of the code, you can construct the tests to take advantage of that. And once you find out what's wrong, you know where it is. The disadvantages, you only test the system as implemented, will not catch missing functionality. In other words, you can miss tests. What if you didn't implement a requirement, or you forgot to document a requirement? So the customer had some functionality they wanted, you didn't capture it in your requirements. Well, you sure as heck aren't going to code something that's not in your requirements. So again, you can't prove that your software is correct because you may have had a problem further back in the process. And the other disadvantage is it requires actual system implementation to develop test cases. So there are techniques you can use to perform testing on software before the testing is built. And this is not one of those techniques, right? You actually need the actual software. Some of you might take SE300. SE300 is about formal modeling of software. And in that class, they talk about how you can, even before the software is coded up, people should design the software first. And if you create a formal model of the software, it's a simulation of the software, or a mathematical representation of the software. You can perform some testing immediately, well before the software is coded up. Okay, statement coverage. Select test cases so every statement is executed at least once. It is not the strongest case here. So in this case, what do we have here? Read A, B if A is less than 0 or B is less than 0, then you go through 3. So what you're going to do is pick situations where on line 2, if A is less than 0 or B is less than 0, where A is less than 0 or B is less than 0, that would be a test case. And that will throw you over to the branch 3, 4, 5. And then you pick one where A and B are both 0. That would be a test case, and that would throw you away from that whole if then else branch with the loop in it. And then go down to 6. Inside of 3, you would have test cases. Inside of that 3, 4, 5 branching, you would have a test case while C is less than 100. You would have a test case where C was greater than 100, C is less than 100, again, going through the loop. And you may have test cases where C starts out less than 100, but then as the loop progresses, it gets larger and larger. So we have specific test cases, right? We don't need to go through those. Okay. It's easy to do. It is not the best, strongest test. And one of the reasons is there can be some odd interactions between inputs that you missed, and there can be some odd interactions between statements that you can miss. So if you're doing, in order to get down this branch, well, I'll talk about that later. Branch coverage, this is a little more common. Now you're going through and making sure every edge on your control flow diagram is touched, executed at least once, and tested at least once. So here, you're going to want to have, see these independent paths, 1, 2, 3, 9, 1, 2, 3, 9. 3 was, remember, oh, we don't care what it is. It's going to be a loop. But it's possible that you never enter the loop, right? So you execute 1, 2, and 9. It's also possible that you enter the loop, but you don't ever see line 6. So in that case, your path would be 1, 2, 3, 4, 5, 7, 8, and then 3, 4, 5, 7, 8, 3, 4, 5, 7, 8, right? That keeps happening for as long as you want it to, and then back to 9. And then in the last version is it's possible that you entered the loop and you actually, on line 5, which was an if then else, went to node 6. So you get the 1, 2, 3, 4, 5, 6, 7, 8, and then kicks out to 9. So there's 3 different paths. You would come up with test cases that made sure that you hit all 3 of those paths. This is a little stronger than line by line. And here's where it's stronger. Let's say you did the path in the middle, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's clearly every statement. So if you did statement coverage, then you have achieved your goal. If you only test that path, though, it may turn out that the conditions that required you to go to node 6 were screwing something else up somewhere. So when you went 1, 2, 3, 4, 5, 7, 8, 9, you got a bad result. But you would never know that if you did statement coverage and not path coverage. And as these things get more sophisticated, people even talk about you shouldn't just do every path, you should do all possible combinations of paths. Well, if you know your combinatorics, that can lead to a large number of test cases. Okay, we're not going to do this. Minimal set of test cases. We're going to just look. We want to make sure to get the path 1, 2, 3, 9. How can I get the path 1, 2, 3, 9? Well, let's see. If result is less than 0, well, let's make result greater than 0. Okay, so I'm at 1, 2, 3, 9. All right, result equals 5 is greater than 0, so that's 1, 2, 3, 9. And then to get 1, 2, 3, 4, 5, 6, 7, 8, we want, what do we need for 3? Result is less than 0, and 5 is x is greater than k. So what was a, DC stands for don't care. Oh, that's the first test. Here's the second test. Result is less than 0, so -1. X is greater than k, so x is 5 and k is 3. That gives you that path. And then for the last one, result is less than 1. X is less than k, so they're going to say 10 and 15. And that gives you that path. So there's 3 different test cases to give you that path. Does this make sense? Path coverage. What questions?
Yeah, it
Path
seems
coverage.
it seems kind of like it'd be difficult to apply to more abstract codes that aren't like mathematically based, you know?
Do you have an example in mind?
So I'm thinking of hours where we like, you know, send a request to Canvas and then receive back certain information. I guess that would be a black box thing because
Yeah, you could do,
we're
yeah,
interfacing
that could be
with
black
Canvas.
box. Yeah, that's a black box. If you're interfacing with another system and you don't have the source code for that other system, that's black box. You can only do white box on your code.
Okay.
But even if the data types are not purely mathematical, you know, at some point, every branching condition is based on a Boolean. And so you have to come up with a Boolean true-false statement, a proposition that evaluates to true or false. So that has to happen, and you create test cases for that.
Okay.
Okay. When I tell people, oh, for for this class, I only want you to do some requirements definition, not all of them, and only run some test cases, not all of them. Can you see why I say that, right? Especially in CS 225, I require 5 requirements and 3 test cases per requirement. Nowhere near full coverage. If you wanted to get path coverage, right off the bat, there's 3 test cases that would have to occur just to do the path. And we haven't even determined, I mean, really all we've done is determine the decision point values. We haven't put in test data to prove that the correct results are coming out yet. So you can see when you start to think through all the different possibilities, hopefully you can see that the number of tests can just grow and grow and grow. That's okay, build them one at a time. All right, so branch coverage, you have to build that CFG, the control flow graph. Condition coverage, now this is a little bit, it's very similar, but now what you're doing is rather than trying to verify that you covered all the paths, you are going to verify that you exercise the true false branch on every decision point at least one time. Now I can lump if then else and loops in there at the same time because an if then else is a one-time decision point, right? And what's a loop? A loop is a repeating sequence of statements. Every time it comes back, it has a decision point. Do I go through the loop again or not? So you want to make sure that every condition was exercised with a true value and a false value. Same trick, you need to identify where the decision points are. It doesn't necessarily mean you're going to get all the paths, because getting all the paths mean that you have to line up certain decision points in a specific sequence in order to get this path. And you're not doing that here. You're independently saying, well, I tested that one both true, false. I tested that one both true, false. I tested that one both true, false. So you're not guaranteeing that you have the path coverage, but you are identifying that you did, at least the true and the false branches. I think this is for a small homework assignment when you're doing your informal testing, the test plan that you didn't write down because you didn't have time. I hope you at least do this where you check, gosh, did it work right for true? Did it work right for false? For a small homework assignment, coding assignment, that tends to be a doable thing to do. We all know logic, right? So our and condition, we have 1, 2 is A equals 0 and B equals 0. Oh, okay. So what do you have to check here? You have to check at least 3 test cases. Now, how many possible combinations of A and B can you have? 4, 0, 0, 0, 1, 1, 0, 1, 1. 4 different test cases. But since it's an and, if the A is not equal to 0 or the B is not equal to 0, those test cases will collapse into 1, and the only one you get is the A. I should say it this way. A equals 0 and B equals 0 is one test case. That's the only way that can happen. If A is not 0 but B is 0 can be a test case, and A be 0 and B not 0 can be a test case. And the fourth one would be A not 0, B not 0. But you probably won't test that one. He's checking here, 1, 2A, 2B, 3, join, 1, 2A, 2B, 4, join. So he's breaking line 2 up into 2A and 2B. And notice what he does with 2A, 2B. If A is true, then you have to test B for true and false. If 2A is false, you don't have to test for B. And so that's where he's collapsing. Hey, if A is false, that whole thing is false. Therefore, I'm not going to test it. I'm not going to test A false, B false. But if A is true, I'm going to test for A is true and B is false. The OR condition, breaks it up again, A equals 0 or B equals 0. So he breaks it up into 2A and 2B, where 2A is the A equals 0 part, 2B is the B equals 0 part. And now you have to check, okay, if A is false, you're not out of the woods, because if B is true, then you're going to go do line 3 there. It's almost the, is this the opposite? Is this a flip-flop version? Not quite. Oh, because he changed the code on you. Otherwise, it is a flip-flop version, right? Yeah, but if A is false, you go over here. If A is false, 2A is false, you go over here to 2B. So in other words, if A is not equal to 0, then that whole thing, then so far we have false, we'll go over here. And now we'll check if B is equal to 0. And if B is equal to 0, then you have to go here. So you have to play around with these graphs to make sure that you're catching all the different conditions. Now, these conditions, how often do you get these combined conditions and how complex do they get? Number one, have you guys used these compound conditions anywhere in your code at any point in time? I would think almost certainly yes. Yeah, I would think certainly yes. Now, have you made it more than that? Have you made them bigger than that, where it's A or B, right? Condition A or condition B and condition C or condition, you know, have you made a big long preposition? How ugly has it gotten in there? Okay, here's my recommendation. If you get more than one logical operator in there, you break it up somehow. And even if that means, you know, in a legitimate way to do this, by the way, is to write a method for it, and you make a method call rather than putting that in there. Often if you have these big long things inside of your single if then else, there may be a design problem. You could maybe design your way to a cleaner solution. Sometimes you can't get around it. It's just ugly, but use different formatting than that so that people have a better chance of trying to read it. And or, yeah. Michael's just laying out all these logical connectors. This is pretty common though. You know, if you write code of any size, it's not too uncommon to have an and or an or in there. So that would be where you're going to be developing you can develop test cases to make sure you're doing right both all possible conditions that make that true, all possible, no, I shouldn't say all possible. A condition that makes that thing true, a condition that makes that thing false, and all the variants thereof, not every single possible instance, but not every input, because that's impossible, but like sentinels or representatives. Okay, some other approaches: path coverage. Every distinct path code, we talked about that. Path code is at least once. Def use. Actually, no, path coverage is different than branch coverage. That's what we talked about before. Path coverage is all, you take all the combinations of branches you can have and make sure you get them right. This is a pretty good technique because, like I said, let's say you go into line 7 here and you go from 7 to 8. And the way you got there was 1, 2, 3, 4, 5, 7, 8, and it works. But it turns out that if you went 1, 2, 3, 6, 7, 8, it didn't work. You may not catch that if you just did branch testing. But if you do path testing, all possible paths through the entire code, then you would catch that. Now, why would that happen? It may be that the conditions that arose that made line 3 read false to take you to 6 still persist. And so when you're doing line 7 going to 8, it turns out that that weird condition of whatever made line 3 false and whatever made line 7 true is a weird combination of data points that make line 8 wrong or make the result wrong. So path coverage. Def use coverage. We don't need to talk about that. other than the definition is when you're giving a value to a variable, and a use is when you're using. And so some people want to test every possible combination of I assigned a value, I used a value, I assigned a value, I used a value. Okay, black box testing. As we said before, black box testing is about, we don't know what the code structure is like. We just know there's input and output. You can test this now, not just at the unit level. Now you can test it at the integration, the system, all the way through. So the larger the system, you just draw a bigger box around what you're calling a black box. Disadvantages, no sense of how much the system has been tested. Again, remember how all these techniques we talked about before were basically coverage. We're trying to get every line of code. We're trying to get every path. Well, if you don't know what the lines of code are, you don't know what the paths are. So you don't know how much of the system you actually exercise. There might be large chunks of the system in that black box that you never actually executed during your test suite. And of course, if you find it, you don't know where. All you know is the output is wrong. Well, why? Right? Could be anywhere in there. The screw up could be anywhere in there. Here's the advantages. Test cases can be defined before the system is implemented. That's nice. Can do that. Not just requirements, but the actual test cases. And we're going to talk about equivalence and boundary value testing. These are the two most common. And equivalence testing, I'm sure you all remember from CS222, the idea of an equivalence class. Anybody? Who had CS222 when I taught it a few semesters ago? I think several of you were in that class. Don't worry, I won't put you on the hook. Equivalence classes, here's what they do. They take a set, any set. And if you can impose certain properties on that set, you can divide that set up into a set of equivalence classes where every element of the original set belongs to one and exactly one equivalence class. So you're partitioning the set into these subgroups. And inside of each subgroup, which we call an equivalence class, is some of the members of that original set. And here's the good part. You can randomly take any one element out of that set and treat it exactly as if it was all of them. It will behave with respect to the equivalence relation. It will behave exactly like any one. Now you can imagine how this is a good thing for testing. For testing, instead of having to do a million test cases, if I can prove that they're all part of the same equivalence class, I can do one test case. And it's mathematically been proven that that one test case behaves just like the other 999,999. Therefore, I get a lot of coverage with that one test. So that's what equivalence class testing is about. Picking your inputs or your test conditions in such a way that they are representative of a class of inputs. And it's not that tough. Okay, this is what I just talked about. You're partitioning, you can partition any set, but the set that we're interested in is the inputs, right? The test conditions. So you're partitioning all of your test cases, all of your inputs. So here, if X is greater than Y, then S1 else S2. Now what's happening, you have partitions, X, of all possible inputs, X, Y, right? They're ordered pair X, Y. They're going to be partitioned into two groups. Either X is greater than Y or X is not greater than Y. X is less than or equal to Y. So if you pick one test from X is greater than Y, one test from X is less than Y, then you have covered the entire spectrum, at least with regard to branching. Now the problem is, note the contradiction. These input cases, we're talking about black box testing. We don't know if this X greater than Y statement is in there. So how do we figure that out? That has to be part of the design. Hey, here's the behavior I want. If these set of conditions are in effect, this is the behavior I want. If these set of conditions are in effect, This is the behavior I want. And now I can, test for both those sets of conditions based on not the software code, but the description of the functionality, the description of the input-output behavior that was desired by the customer or by the designer. We're not going to do that one. Are we? Range of values of range of x values. X is, oh yeah, x is from 1 to 50 returns true, otherwise it's false. Now, what are the range of values of x? Well, assuming x can be less than 1, assuming it's an integer value and it can be less than 1, then our true, if I'm reading this right, our true class should be 1 through 50. Our false would be anything less than 1, anything greater than 50. So there's 2, right? Less than 1, greater than 50. So 0 and less and 51 and more. If I'm reading that right. And, our friend Ochoa may have tricked us. So here we are. 1 through 50 is an equivalence class, which means we would have 3 test cases in this case. Maybe -10, 25, and 60. Now we're going to get a little better at that in a minute. So this notion of equivalence class, you're chunking up where the boundaries are. Now here's a question. Wait, I'm going to go through boundary first. Okay, so then here we have these other partitions. This program specification states accepts 4 to 10 integer inputs, which are 5-digit integers greater than 10,000. X is the number of input values. 4 to 10. Oh, okay. So now you've got a range of how many inputs you have and their actual values, and you can try to partition that. I'm not going to go through the math. Yeah, we should do that. We should go through the math. There are, well, there's, what do we got? 4 through 10, and greater than 10. Less than 4 through 10, and greater than 10. That's 3 equivalence classes. And then we have Y less than 10,000, 10,999, greater than 10,000. So the minimum, you would need 9 tests there. Right? Each equivalence class, that X less than 4 would get paired with the 3 Y values, equivalence classes. The X's 4 through 10 would get paired with the 3 Y value equivalence classes. So that would be the minimum of 9 there. You can start to play all kinds of games though with, if I have 5 inputs, in this case I have 5 numbers, right? They're all greater than 10,000. If I have 5 inputs, what if only one of them is less than 10,000? What if 2 of them are less than 10,000? Right, that kind of thing. You still can run away with problems. Now I'm going to combine this equivalence class testing with boundary value testing, and you guys have done boundary testing before, I hope. Where do you do boundary value testing typically? I haven't defined it yet, but you can guess what it is based on its name. You're testing everything at the edges, right? Testing everything. You've done that boundary testing. I'm going to guess when you create a for loop, hopefully you've created it and ran it, even if the test was informal, to make sure that it worked at the boundary conditions, that it worked if you had no times through the for loop, at least one time through the for loop, or what was happening the last time through the for loop. Usually your for loop is tied to an array. So you wanted to make sure the first time through the for loop, you were at the first element in the array, and the last time through the for loop, you were at the last element of the array, or wherever you wanted to be. That's where boundary condition testing occurs a lot. Hopefully you tested your arrays too, that you always went to the, you checked that you could assign and retrieve from the first element and the last element, because what's a common error? Array out of bounds condition, right? So that's really a form of boundary value testing. So here's where boundary value testing can work. Let's say you had we're doing aircraft and we can have an altitude of 0 to 50,000 feet. Where's the boundaries? Well, 0 is a boundary. So you always test a little to the left of the boundary, at the boundary, a little to the right of the boundary. So if it's integer based, I would test -1, 0, and 1. And then at 50,000 feet, I would test 49,999, 50,000, and 50,001. These are the boundary testing. You're basically, you go right up to the boundary, at the boundary, crawl across the boundary, and test to make sure that things are fine. Now, if you combine that with equivalence class testing, that means that you can take at the boundary, below the boundary, that element below the boundary served as a representative of everything below the boundary. And at the boundary serves as a representative of everything at the boundary, which is typically 1 value. Inside the boundary, 1 inside the boundary, almost serves as a representative of everybody inside the boundary, but actually right at, 1 away from the boundary condition is actually not an interesting case to take. So if you have a range of values, 0 to 50, 7 test cases is a normal thing: below, at, above, in the middle, below, at, above the upper bound. That's a pretty normal way to go. So you can take equivalence testing and boundary value testing and come up with a good set, right? Here's, we identify the equivalence classes, the boundaries of each equivalence class, and now you're going to do, right? So here, less than 10,000, between 10,000, right? So now in this case, I don't care what Ochoa says on the next slide, I would do, let's see, 999,999, right, to get, and then I would do 10,000, then I would do 10,001, then pick somewhere in the, somewhere away from the boundary, like 50,000, then do 999,999, and then do, I'm sorry, 999,998, 999,999, and then 100,000, 1,000,001. So you get those test cases. Okay, so there's your boundary value testing. And then the only test I added was 1 in the middle. And the reason is sometimes I would argue the ones in the middle are not quite in the same equivalence class, because sometimes there's some odd effects from being close to the boundary. Now this is, I like this one. 0 to 15 don't hire. 16 to 18 can hire as part-time. 16 to 95 hire as part-time. 65 to 99 don't hire. How do you plan the tests? Well, there's all your boundaries, right? How do you plan the tests? Well, we should plan, right, at these boundaries. 14 to 15, is that a boundary? Right, the boundaries between 14, 15, 16, 17, 18, 19, 20, 64, 65, and then 66, let's say. So you go 14, 15, because you're below the boundary and at the boundary. 16, 17, 18, because 16 is at the boundary, 17 is next to the boundary, 18 is at the boundary, right? The boundaries are between 18 and 19 here. 19, 20, and 65, 65, 66, 69. I think there's a typo there. I think this line is supposed to be 66 based on his test cases. So those are your test cases. And then 100, should you do that? Maybe you should. Why would you do 100 as a test case? Are any of you old enough to remember the Y2K scare? What's unique about 100? 3-digit number, not a 2-digit number. That can matter. Not in numeric systems, but it can matter if, remember, when you fill out forms, everything is always text. What if you assumed everybody was between 0 and 99 and you only allowed 2 digits for age, and then someone comes along that's 103? Oh yeah, that happened. That's what the Y2K was about. Everyone had 2-digit codes for the year, and then they realized, oh shoot, when we roll over into the 2000s, we're going to have a lot of people who were born in the future because they claim they were born in 35, and we don't know if that's 1935 or 2035 in the software. Or if you're in 2004 and someone said their birth date was 03, are they 1 year old or 101 years old, right? That was a problem. Now here's the problem here though, this don't hire about, and what's being pointed out here is the test was good, but is there any problem with this? Did anybody flag? I got a red flag when I read this slide. Did anybody get a red flag when they read this slide? But just me? It's because I'm getting older.
If you're 100 years old, there are no rules for you.
I'm sorry, say that again. If you're 100 years old, oh, there are no
nothing
rules.
applies. Yeah.
Have you heard of age discrimination? What if someone's 65, perfectly capable of working, perfect for the job? Sorry, our policy is if you're 65, you don't get hired. We're going to hire a less qualified candidate who's 47. Ah, there's weirder stuff than software in the world. So that may be a bad, right, ethics stuff. That may be a bad requirement right off the bat. And there have been, again, you can find situations, people who are forced to retire at 65. Our company policy is if you're 65, you must retire. Usually they don't make it 65 because that's a lawsuit waiting to happen. They'll usually make it more like 70, you know. So there are issues with some of that stuff that we didn't catch, right? We were so focused on the test case, we didn't ask, is the requirement any good? Which shows you again, you can pass all your tests and still have a problem. You can still have bad requirements, which would result in bad software. Okay, that's it. Questions before we go? Comments, concerns? Yelling at me for grading late. If you want to hold off on your sprint 2 deliverables till I give you some feedback on sprint 1, that's fine. It should be within I should get those out tomorrow unless tomorrow has some kind of crisis. Although I think I've met with teams and I've been giving feedback informally, so hopefully that's helpful. But yeah, if you want to, you know, by the time I give you your date, let's say you give you 2 more days after that, that's fine. You can still hold your sprint planning meetings and stuff. That's just documentation that we're worried about for that deliverable. But if you can still meet with your TAs and again, I sat in, I think, on 8 meetings last week. So I'm trying to get to everyone, and I plan to continue meeting with people as the semester goes on, especially since, you know, in a few more weeks, there's no more lecture. So even this time will be available for informal discussion and team meeting. Okay. Other questions, comments? What's on your mind? Okay. I will see you guys during your team meetings this week, and then see you here again on Monday. And oh, Team 12, I think you guys meet right after this. I won't be able to join that meeting this week. Have a good one.